you'd probably guess it was a PNEB. Our speaker, again, is a very interesting speaker, a real live JPL planetary scientist who has been working on a number of missions dealing with the formulation, design, and planning of planetary missions and missions to near-Earth objects. She's the principal science investigator at the JPL for the Near-Earth Asteroid Scout Mission, and she's French. She earned a PhD in planetary geophysics at the University of Rouen in France, and she's been at JPL since 2007. So I will ask Dave if we have managed to solve the connectivity problems.
I can see her. Yeah.
Is she there?
She's online.
Julie, you made it.
Just like 10 seconds ago, sorry.
I'm so sorry we had the problem. We should have done an experiment in advance. I'm used to doing Zooms from Caltech, so I'm sure you could have gotten in on the Caltech system.
Yeah, sorry, I didn't think about checking that, but yeah, JPL has these strange rules, but I'm glad I made it.
Was that a good enough introduction, and did I pronounce your name correctly?
Yeah, perfect, thanks. I work at JPL, but I've not been at JPL for the past 18 months. JPL right now only allows people who are essential, so people who work on the missions, like the Mars 2020 missions. These colleagues, they can go to JPL, but because I work on the missions that's coming later, I don't need to go to JPL. And so the workforce is limited to about 1/3 of the total workforce, or about 2,000 people. But I live very close to JPL, so every day I walk my dogs just next to the place, and I took this picture for you earlier today. And it's really a very nice place. You see, it's really seated in the mountains. There is a big river, although of course it's very hot here. So right now it's dry. And sometimes we have snakes, like this king snake that we found with my family a couple of days ago. So, but otherwise, I mean, there is a lot of very nice wildlife. So we love it. Next, please. So yes, I've been at JPL for 20 years. I came in as an affiliate on the Castillo-Rogez mission. And so I learned the operations for missions then. And then I've been involved in a variety of missions. And especially I'm still a little bit the deputy principal investigator on the Dawn mission, the mission that went to asteroids Vesta and Ceres. So I was there for the Ceres phase of the mission, and now I'm leading future missions to Ceres, and we're talking about bringing back a sample or sending a lander. And I'm also involved in a mission to the Europa, the moon of Jupiter, Europa, and I've been working on other kinds of missions. It's very fun to be at JPL, and something I like very much is that we meet a lot of technologists, and there is an opportunity to work on a variety of topics. And so in 2013, I got involved in the development of CubeSats. CubeSats are very small spacecraft. They are about the size of a shoebox, so very small. CubeSats were born in the universities. They were originally used to train students to develop spacecraft, but then there was a big interest in exploring how we can use CubeSats for deep space exploration. And I became involved in the Near-Earth Asteroid Scout Mission, and it's been very exciting. It's been a long way, and we delivered the spacecraft just last month, and we hope to launch at the end of the year. So I appreciate very much your invitation. I'm very excited to talk about this mission. Next, please. So NEASCOUT targets near-Earth objects, or near-Earth asteroid. And there are many motivations for exploring near-Earth asteroids. One is just that they are very interesting from a science standpoint. Near-Earth asteroids, they were born in the main belt of asteroids between Mars and Jupiter. They are fragments of main belt asteroids that were ejected by impacts. So regularly, main belt asteroid is impacted by another main belt asteroid, and this ejects material in space, and that material, some of that material gets to Earth region. And so it's a way, if you want to studying near Earth asteroids, it's a way to sample main belt asteroids and learn more about the origin of the solar system. There is also a huge interest in understanding near Earth asteroids because they can be potentially hazardous. I don't know if you saw the headlines just like last week. Bennu, the target of the OSIRIS-REx mission, was found to be a potentially hazardous asteroid, which means that sometime in the future, and it might be 100 years, it could get really, really close to Earth. And so we are watching for these asteroids. There are a lot of activities at NASA for making an inventory of these objects. And so I will mention that a little bit later in more detail, but part of the NEASCOUT mission is motivated by human exploration, but what we will learn will also help understand how we can mitigate impacts from near-Earth asteroids. And so the Near-Earth Asteroid Scout Mission is sponsored by the Human Exploration Program at NASA. That program to explore asteroids was of great interest about 10 years ago. It's of much lesser interest now. The moon is really the next step for human exploration. And then, of course, NASA wants to send astronauts to Mars. And personally, I mean, I find it very good that NASA and hopefully, other countries are interested in going back to the moon. It makes totally sense to explore the moon. But I'm also very grateful that despite the change in focus of the Human Exploration Program, they've been funding us till the end, and they really wanted that mission, our mission, to succeed. I'm very grateful for that. And lastly, there's been a big interest, as I'm sure you know, in exploring near-Earth asteroids for economic purposes. I think 10 years ago, it was really trendy. It's much less trendy now. But again, what we will learn with the Near-Earth Asteroid Scout Mission can help that particular kind of endeavor. Next, please. So just to show that we've been very lucky with ground-based observatories, because here you see the number of asteroids discovered, NES discovered, as a function of time. And you can see that before year 2000 and about 2010, there was a low rate of discoveries each year. But then there have been several big changes, and especially the introduction of the Catalina Sky Survey in green. So sorry, so I forgot to mention that these are discovery spare type of telescopes. So the Catalina Sky Survey has played a big role in inventorying the NEA population. And then just a few years ago, there was the introduction of Pan-STARRS. And Pan-STARRS, it's a big telescope that's located on Maui. It's amazing. That's the telescope that is responsible for finding interstellar objects, for example, and the big long period comets. So it's just tremendous. And so you see there is a big increase in the discoveries of near-Earth asteroids over time, which is great for us because we need targets. As I'm sure you know, we're flying with Artemis 1, the first launch of the Space Launch System, and we were supposed to launch in 2017, but our launch window has been shifting over time because the SLS is not ready, which has been very good for us because we've had plenty of time for testing, and also we had to deal with delays because of COVID. And so, but then our targets have been changing. They've been disappearing over time, but thanks to these programs, we've been able to find new targets for NEASCOUT. Next, please. And that just to show the census of asteroids. And so there are a few near-Earth asteroids that are bigger than 1 kilometer, very few. But then there are many asteroids that are less than 100 meters, and that's the population that we are targeting. So it's a good thing. There are many of them, but they are very small, and our target is only between 5 and 15 yards in size. And but at least we have some choice. Next, please. So okay, so I'm going to present NEASCOUT in more detail. Next. So sorry, I should mention that the mission is developed at the Marshall Space Flight Center in Alabama. JPL is a partner. At JPL, we take care of the avionics, the instruments, so all the electronics, the instruments, and the science and so on. But Marshall is doing the bulk of the work on the flight system. And that's the Marshall team. I really want to acknowledge these guys because you see their mask, not just because they are in a clean room, they are masked because of COVID. And so this team has been working under very stressful conditions. All our integration and testing happened during the lockdown. And so they had to deal with, so all kinds of rules. They had to deal with the fact that they had people sick in their families, and it's been very stressful, but they really delivered, and I'm very proud to be part of this team. Next, please. Okay, so NEASCOUT is one of 13 CubeSats that will be launched with Artemis 1. This information for 2020 is already obsolete because we heard earlier today that the launch now is delayed to December, really December 20, so the end of the year, and might be delayed further. It's not clear, but we are getting very close, that's for sure. It was selected in 2013. Sorry, these are technical details. It just means we had a bunch of reviews. But what's important is that it's fully integrated and tested, was delivered to the Cape, to the Kennedy Space Center in July. And at this point, it's integrated on the upper stage of Artemis 1, which is very exciting. The main goal is to characterize the near-Earth asteroids. There is only one imager, but I will show you that it's sufficient to really get a lot of information of interest for to prepare for human exploration. And of course, when we started working on this, there was also a great interest in just demonstrated low-cost missions, so that we hope this one is going to be very successful, and then we can make many of these small spacecraft and decrease the overall cost of space exploration. That's the long-term goal. We are leveraging a lot of past projects, and especially my co-PI, Les Johnson, has been working on various solar sail missions. The Planetary Society also has one mission called Light Sail 2 that's currently in flight. We're leveraging a lot of developments for CubeSats from universities. I'll talk a little bit about that. And then just so that you understand the constraints we are dealing with, it's a 6U CubeSat. So 1 U is equivalent to 1 liter, 1 quart. And so this is about 1.5 gallon flight system. It's extremely small, but it includes a very large solar sail, which is close to 100 square meters. This technical, it's just that, most of what we have put in NEASCOUT, it's something that was not necessarily certified for deep space. There are a lot of things that, were commercially available. And because of that, we have to limit, we know that we can fly for about 2.5 years, and that puts a time constraint on our mission, but that's not a problem. And we also have, as you can imagine, when you have a tiny spacecraft like this one, we don't have a lot of telecom capability, and so we need our target to be very close to Earth, and we are lucky right now because we hope we can keep our current target, and it's going to fly by very close to Earth when we encounter it. And lastly, so the thing that's amazing with a solar sail is that it goes really slow. We are going to be able to achieve the slowest flyby of any object achieved to date. Next, please. So our goals, and I'll just go fast on this. So our goal is to get information that retires what NASA calls knowledge gaps. for human exploration. So like we would like to send humans to near Earth objects on near Earth asteroid, and we need to know the location of the object, the size, its rotation properties. That is very important because you know, the near Earth asteroids, they spin really, really fast. We want to see if there are hazards, particulates, environments, debris. We want to understand if an astronaut sets foot on a near Earth asteroid, you know, is he going to sink? You know, is the surface stable? So that's kind of the information we are looking for. And then we're looking for morphology and so on. And here is just to show how this information helps. And so we want, you know, we need that kind of information for the safety of the crew and mission. And that's what's in blue. Operations, we want to optimize operations and decrease cost, increase performance, and be able to carry out some science. And so that's the rationale behind getting all these pieces of information. Next, please. And so here it is. So we're going to send NEASCOUT at the end of December. We're going to stay in the Earth-Moon system for about 6 months, and then we will take a gravity assist to catch our target. And we take the gravity assist at the moon. So once we are past the moon, we are going to be in cruise for about 18 months. And then we will have our target in sight. And so it's not clear yet how it's going to work out, because our target has been a moving target because of the change in launch window. But we think we can start looking for it about 2 or 3 weeks before the encounter, or about 40,000 kilometers. And so that's what that will be the first big science activity, is to search and detect the target. Once we found the target, we will start our approach phase. We'll keep observing the target on a regular basis. And when we are about 100 kilometer distance, that's where we have resolved images of the target, and we start getting the science information needed for the strategic knowledge gaps. And so we'll be able to image the entire surface at relatively good resolution. And we use that information to then infer the target spin rotation properties, its volume, its morphology. And then at some point we can do a very slow and very close flyby of less than 1 kilometer. And then we'll get this kind of images where we have a very good resolution of the surface, and we can see the boulders, and we can see, you know, where there are stability issues on the surface and so on. And then at that point we'll be gone. We cannot get in orbit around the target, but we will we'll stay very close for a couple of hours. So we are going to investigate very, very in great detail. Next, please. And so, as I said, the Near Earth Asteroid Scout Mission leverages past technologies, and especially, you probably heard about the MARCO mission that JPL sent with the InSight mission to Mars a few years ago. And so it was great because MARCO, which is, I'm sorry, I cannot show my cursor, but that's on the left side, bottom left side, that's the spacecraft with the big antenna, the orange antenna. And so MARCO is great because it demonstrated a radio that we can use in any scout. And having telecommunication is really the primary thing you want when you have a spacecraft. You want to be able to communicate with it and then use the radio to navigate the spacecraft. And so we are in the phase where we are demonstrating the CubeSat technologies. And the idea in the next stage is to enable space exploration at lower cost. And so, and hopefully, I mean, and the long-term goal is to explore, for example, the deep oceans of the moons of Jupiter and Saturn, because this phase of exploration with NEASCOUT is really pushing the boundaries in terms of shrinking electronics, for example. So we have much smaller electronics, much smaller instruments, we have better propulsion systems. And so the idea is to prepare for very challenging missions in the next decades. Next, please. And so in the case of NEASCOUT, we are introducing the propulsion with solar sail. And just to give you an idea of the scale of the solar sail when it's deployed, and in comparison, as you see on the bottom right, the size of the spacecraft when it's folded, before the solar sail is deployed. So it's tiny spacecraft. It's the tiniest spacecraft sent beyond the moon, but then when it's deployed, it's the biggest spacecraft sent beyond the moon, basically. So it's just a really cool mission. Next, please. And the idea with the solar sail is that it uses a thrust from solar radiation and solar light, which is a very tiny push. But it keeps, if you want this acceleration, it keeps, it's continuous. And so when you keep pushing on the solar sail for a very long time, after several years of flight, you can reach velocities that are up to 5 kilometers per second, which is huge. This is very large. And so that's because you have this continuous push on the sail. Next, please. And so NEASCOUT is going to be mounted on the Orient stage adapter. So one of the upper stages of Artemis 1. And you can see as this stage has a bunch of CubeSats, and they will be deployed. I'm very sorry because the next slide was supposed to be a movie. So I think we're going to pass. So if you can go to the next. But you have the link if you want to look at the movie. It just shows the stages from launch to deployment of NEASCOUT. So unless you can play it now. Okay, so the NEASCOUT, it builds on a big interest in the development of solar sails. And I want to acknowledge my colleague, Les Johnson from Marshall Space Flight Center, because he's been the primary person responsible for pushing the development of solar sails. And by the way, he's an amazing speaker, and he's also a science fiction writer. If you have an opportunity to invite him, I mean, he is just awesome. And so yeah, you see here is playing with some solar sail material. It's only 2.5 micron thick. And basically Les has been behind, I think, most of the solar sail missions that have been developed by NASA. And so there is, except for Light Sail, which is developed by the Planetary Society, but we're working with them closely. Les is one of the lead, or maybe the lead for the NASA in Space Propulsion Technology Project. And then he was the PI, the principal investigator for NanoSail D. And then he's a co-principal investigator with me on NEASCOUT. And then the idea is that we are going to leverage what comes from NEASCOUT and then allow bigger missions, bigger sails. And Les is the lead on a mission that was recently selected, which is called Solar Cruiser. And it's going to be a huge solar sail, much, much bigger than NEASCOUT. I think 1 order of magnitude bigger, and that spacecraft will get very close to the sun. It's going to be exciting. Next, please. So the principle of solar sail navigation is like when you solar sail boat. You have this big sail and you want to orient it with respect to the wind or with respect to the radiation from the sun. And so for NEASCOUT, we had to develop a system that allows pulling on the sail so that it takes the orientation that we want and goes where we want it to go. And that's what's called active mass translation. I mentioned this because it's a very complicated system to implement, but in practice, it's like pulling on, you have the ropes on the sails. and then you just pull them one way or another, and that will help you go the direction that you want to go to. Next, please. Okay, and that's our spacecraft. So it's tiny, but it has a lot of things. So I'm going to go from bottom left to bottom right. So first, you see, we need solar arrays. If we go to space, we need power, and so we have solar arrays. They can be retracted, and so they don't take too much space. So that's good. About half of our spacecraft is for propulsion. It's for the solar sail and everything that goes with it. So I said we need ropes, and we have ropes, and they are handled by that active mass translator. We also need cold gas, because we need to do some maneuvers, like when we want to take the gravity assist at the moon, we need to go a bit faster than what the solar sail gives us. And so we need some more, the more active propulsion, that we get that from coal gas. We don't have a lot, but it's very, very much required. And then we need batteries. And so the upper part of the spacecraft is where you have all the avionics, all the electronic. We have batteries, which are very close to batteries you use in regular equipment. We need sense sensors. These are very important. If there is any failure on the spacecraft, the sense sensors will always orient the solar panels towards the sun so that the spacecraft has power while the team on the ground is trying to debug, to troubleshoot the spacecraft. So sense sensor might be the most important piece of equipment on this spacecraft. And you have the imager, which is tiny. It's half a liter in volume, it's very small. We need star tracker, which gives us the position of the flight system with respect to the stars, and it gives us the attitude, and that's very important to know where we are and where we are going. LGA, these are the antennas, so that's our primary mode of communication with the ground. And we have another antenna, which is a medium gain antenna, MGA, that you see on the bottom right, and which is on one of the solar panels. That's when we want to downlink a lot of data. What we call the IRIS-2-1 transponder is a radio. It's tiny radio that was demonstrated by the Marco mission. And then we have things like IMU and adjust sensors to tell us how the spacecraft is oriented and so on. And we have reaction wheels. Reaction wheels are what helps the spacecraft turn fast. If we want to take an image and we want to turn fast to take the image, we are going to use reaction wheels to do that. Or if we want to point the antenna to the Earth, we also need to use a system that allows you to turn fast. Next, please. And that's just a picture of what I presented now. That's during the testing. And so you can see the 4 solar panels, half of one is being used for the medium gain antenna. And then, then we see a bunch of things. You see the aluminum thing in the middle, that's the solar sail. And a lot of what we see otherwise are just for testing, so sensors and so on during the testing phase. Next, please. And we delivered, here you have a picture of NEASCOUT being integrated in the deployer that was put on Artemis 1. Next. So, as I noted earlier, there are a lot of targets accessible. There are about 4,000 targets that we could potentially reach. In practice, our targets are going to be very small. And so if you look at the chart, it shows the expected or measured size of targets that are accessible to a spacecraft that can go between 0 and 5 kilometers per second after launch. And so, as I told you earlier, we can, NEASCOUT can achieve between 3 and 5 kilometers per second. And so you can see our pool of targets is relatively large, but they are going, our targets are going to be small. They are going to be really between 5 to 50 meters if you want in size. So they are tiny, they are very challenging. But we're working, NASA created a program office that is about finding and classifying near-Earth objects or near-Earth asteroids. And they've been finding asteroids for us. We've also been working with a very large telescope to find targets. Next, please. And our baseline target, it has this weird name, 2020 GE. It's going to get a real name very soon once the launch is confirmed. It's an Earth-crossing asteroid, which means that for a while it was classified as an impactor, virtual impactor of Earth. It might be a fragment of the moon. And so that's something very important to know, that these near-Earth objects that are very small, they could be fragments from the moon, they can be stages from the Saturn V, and they could be all debris from previous missions. And so hopefully it's a real object, and it's not just a piece of junk, but that will be the surprise when we get there. And so we'll encounter end of 2023, but before then, GE will do a very close flyby of the Earth, and so there will be a lot of observations done at that time. I hope your club will be interested in being involved in this kind of activity to look for the NEASCOUT target. We know its position very well at this point, and when it goes by to Earth, it will be very close, so only 0.15 astronomical units. The chart, so it's a bit complicated. It just shows the mission duration as a function of the launch date, and so now we're thinking of launching around January 2022, and you see GE, it's a red curve, and I mentioned earlier, we want our mission to be as short as possible because some of our parts, they are not necessarily graded for deep space, and so GE is perfect. Because if we launch soon, then we could have a mission lifetime that is just less than 2 years. It's good for us. And I just showed the other examples of asteroids that could be backup if needed. Next, please. And just to show the avionics that we delivered. The next pics are really eye candy, just showing the hardware. And so that's the avionics part. You can see the star tracker and the science imager, windows, and the antennas. And that's the JPL team on the bottom right. Next, please. And so I mentioned the radio that was demonstrated by Marco. And so here you have some details. I don't have a lot to say about it, just the fact that it's very compact. And same thing, our computer is extremely small. It's the smallest computer ever developed for space. And so it's been working really well during the test. And so I'm very hopeful it's going to work well when it's sent in the Earth Moon system. Next, please. And that's our camera. So that one is developed at JPL, and I'm the lead of that camera. It's tiny, 400 grams. It's really tiny, but it has a very good performance. We fully calibrated it. There is a spare, we have a test bed, and there is a full spare on the test bed, and just a performance that is really great. And so we use it for science, and we use it for navigation when we get to detect the asteroid. Next, please. And that's a picture. So there were supposed to be an animation, the two pictures on top of each other. If you want, I will send you the PowerPoint later. And just to show you images taken with the camera before and after the calibration. And so it works well, but the thing is that because during the pandemic, we could not, we didn't have a lot of flexibility. And ideally, we would need to take an image from far away, and we could not do that. And so that's the best we could do in the lab. But we were able to demonstrate that the camera is perfectly calibrated, and so hopefully it works. Next, please. And that picture of the flight system, the sail fully deployed, the booms. We have these booms that are very long. Next, please. And more pictures. And so we did tests on the sail to demonstrate that the deployment would be fine. So we do offloading. Of course, we want to limit friction. with the table, and so that's what the balloons are about. And I had a movie that I will send you where that shows the deployment. And you see it's very cool. Huh? So I'm sorry it's not working. Next, please. So yeah, and just more pictures of the hardware. And so you see the cell is entirely folded on the left side, and then you can see the very complex, what we call the harness, very complex wiring that we had to deal with. And as you could see, the spacecraft is really built into these different compartments. And I can tell you the Marshall team had a lot of fun trying to deal with all the wiring, but it's working. In the end, it worked very well. Next, please. So I'm done with the NEASCOUT mission, and I know that I'm at the end of my time. The last slides are just to give you, some information on other missions. You want me to go on, or do you want to stop here and I take questions?
Go ahead just a bit if you don't mind.
Okay, thanks. Yeah, so it's just to tell you, I mean, there is a lot of interest, as I said, in asteroid exploration. So right now we have the OSIRIS-REx mission. That is a sample return mission. Sampling worked really well, and we'll get the sample next year, I think. We have, yeah, so it's all I have on this one. Just to say that it's upcoming, that we are going to get the sample soon, and that will be fun. Next. Another mission that is going to leverage the developments in small spacecraft and CubeSats is called Janus. That one is going to be launched in a couple of years. And the goal of that mission is to fly by binary asteroids. So asteroids that have a companion. And in order to understand the relationship between the main asteroid and the companion. And it's just going to take images and also imaging in the thermal infrared in order to get some idea of the thermal properties of these objects. But it's going to be an exciting mission. It's kind of the next stage in the endeavor of exploring asteroids with small flight system. Next, please. And the big one that is coming soon is DART. So DART is also a small mission. And it's going to launch in the week of Thanksgiving from Vandenberg. And so with a Falcon 9, and I think it's going to be fun. If you have a chance to travel to Vandenberg, definitely that will be a good one. And so if you go to the next slide, please. So DART is going to impact the moon of a binary asteroid. And the idea is to understand how a small asteroid reacts to a kinetic impactor in order to think about future mitigation against near-Earth asteroids that are hazardous to Earth. And so the full spacecraft is going to impact the small asteroid. A CubeSat is going to be deployed and take pictures of the impact, and it's going to follow the impact. So it's going to be nice. So you see it's 610 kilograms at almost 7 kilometers per second. So it's going to be a lot of energy. And on the ground, observers are going to look for a change in the orbital properties of the small asteroid. And that will give us an idea of how the kinetic energy has been absorbed by the asteroid. Next, please. And yeah, the other asteroid mission that's going on right now is called Hayabusa 2. It's a Japanese mission. And it's at the end, I mean, we just received 6 months ago samples. So it was also a sampling mission like OSIRIS-REx, but it sampled a different kind of asteroids. So very soon we have samples from multiple asteroids that we can compare and get information about the origin of the solar system. Next, please. And the last one I want to highlight is called NEO Surveyor Mission, which is a mission led by, I'm sure you've heard of Amy Mainzer with the amazing asteroid hunter. She's been the lead of the NEASCOUT mission, and she's now the lead of the NEASCOUT mission. And that one is just a version of NEASCOUT that's bigger, better, and it's going to look for asteroids in the Earth-Moon system. Oh, I mean, beyond the Earth-Moon system, but especially it's going to give us a lot of information about potential Earth impactor. And so there are all these amazing missions that are complementary to each other. And so there are a lot of discoveries ahead. And thank you very much for your attention. And just to show, yeah, the thing with NEOSM is that it looks in the infrared. So a lot of the sky, the stars are in more blue, but asteroids appear red. And so NEOSM is tailored to look for these asteroids. And so here you have the first asteroid that was found by NEASCOUT. Sorry for the confusion. So that's from NEASCOUT, and NEOSM will be the same kind of mission, and we look for a lot of red asteroids. Do you have questions?
All right, let me stop sharing. Stop sharing.
Thanks much for running the slides for me.
I got it confused when I tried to run the link for the movie.
Oh yeah, I can send you I can send you the real PowerPoint presentation, and it has more information, it has animation, so
okay, thank you.
Yeah.
I have a question.
Mm-hmm.
Does the DART break up the potential collision of an asteroid? Does it break it up into tiny fragments, or does it set it on a different trajectory?
Yeah, I think it's both. So the goal is to set it on a different trajectory and measure that shift in trajectory with ground-based telescope. But on top of that, it's going to eject a lot of material in space. And the CubeSat that is flying with DART is going to observe how the material is ejected from the surface. DART doesn't have enough energy to do more than dig a small crater, really. So it's not going to really break the asteroid, but at least it would be interesting to see this cloud of dust ejected from the surface.
Thanks.
You said you have one primary target, depending on your launch date and the mission duration and everything. How much flexibility would you have, for example, if you choose another target while the mission's going on? Can you maneuver to another one, or?
Yeah, that's a great question. Let's say we launch and then we find out that, find a new target, and it would have been much better for many reasons. It's hard. And one of the things is that solar sail is extremely slow, especially at the beginning. So it's difficult to retarget. I think when it's set on a course, it's possible that there might be targets the same vicinity, and it's possible to do a small adjustment if we know early enough. But if the target is really in a different quadrant of the sky, then there is no way we can catch it, which is too bad, because we would want to have that flexibility.
You said there's a lot of COTS material on the spacecraft itself, on the CubeSat. Are these mostly components, or is the basic infrastructure of the CubeSat and the internal buses and everything, is that more or less COTS?
Yeah, that's another good question. So it's going to be small components. The thing with these CubeSats, and the NASA centers, they have a lot of standards when developing a spacecraft. So even if we wanted to develop a spacecraft cheap and fast, we would not. We really want to make sure that we are going to work. And so the components that are off the shelf, there are only few, and hopefully they are not going to be critical. But otherwise, I mean, a lot of what's inside the NEASCOUT has been tailored. But for example, the solar panels are COTS. Mm-hmm. And a worry that we have is that if we are in eclipse behind the moon, it's not clear that the solar panels, how long they can stay in the very cold temperature behind the moon is one of the questions that we are wondering right now. But it will work. I'm sure it will work.
More questions?
See, there are comments. I know there are questions.
Let's see, we've got some on chat. Let's see.
Oh, thanks for the nice comment.
That was great. Have a meeting for, do you think that we will be able to, we do have people in our club who image asteroids. Do you think we will be able to capture any of this? Will the solar sail be bright enough for us to see it, or?
I'm so glad that you asked, because that's one of the things we are thinking about right now. It would be very nice to be able to see the solar sail and have an independent confirmation that it's deployed. And so we think it's going to be bright to Earth, and at some point I can share that information. I just don't know because our launch window keeps shifting, but at some point we know exactly the orientation of the sail with respect to the Sun and Earth. And we will engage absolutely the astronomical community and to help us observe NEASCOUT for sure. I'll keep you, I'll get back to you at that point.
It would be fun to do.
That would be amazing to see NEASCOUT from the ground. And then something else that I don't know if that would be possible is during the flyby. The flyby will be very close to Earth. It will be 1/6 of an AU. I don't know if it's possible, at least to image the target. I would imagine that it's possible with most telescopes, but I mean, that's something we should discuss at some point.
We should try that. Jerry Hilburn, are you online? He's our primary asteroid imager. Well, I'll talk to him.
I don't see him on here tonight, Ken.
Yeah, he knows how to access the databases and target these. It's a whole world in itself.
Yeah, I know, and I'm sorry because I should know more about that. I'm not an astronomer, but yeah, we at some point we are really going to gear up and have plans to involve the community and for these various events where there is an opportunity to observe NEASCOUT.
Yeah, I'm sure we'd like to try.
Oh yeah, that would be fun. You might be able to see light sail. I don't know if it's something that is of interest, but the Planetary Society has this light sail mission that is very close to Earth. I'm wondering if it can be observed. So I see a question. Yeah, that's a great question. The solar panels into the solar sails, it's something that the Japanese are looking at. So they are looking at ways to do various things with the solar cells. So first, they are looking at solar cells that are 2 orders of magnitude bigger than NEASCOUT for a mission to Jupiter that would happen in the next decade. And they are looking at adding solar cells, so it's for power in the sail. And also, they want to see if we can use the sail as an antenna, so adding wiring for telecommunication. And so if they manage that, that would make this kind of mission way easier. So I hope they will be successful.
There was another question. It's basically from James Brunton. It says, after the encounter, will there be any reason to keep returning data?
Yeah, oh yeah, I forgot to mention that, but that's an important point. Even if we're close to Earth, our telecom system is, it's tiny. And so it will take 3 months at least to return the minimum data that we need for science. And then if we can keep going, then we will try to downlink everything that's on the spacecraft. And that might take 6 months to 1 year. And so, yeah, we have developed autonomous data analysis on board and data prioritization in order to downlink the most important data. that takes care of the science questions. But then if we can, we'll try to downlink everything. And then if everything goes well, we will try maybe to access another target.
I didn't quite get the way you maneuvered. Do you basically use the reaction wheels to move the satellite, and that pulls on the sail? And
so you have, it's like the system of pulley and ropes on a sailboat.
mm-hmm.
You're going to pull on the sails to orient it towards the wind, basically. So you have all these wires, this very complicated harness that's connecting a table, what we call a translation stage. And the stage is going to move one way or another. And by doing so, it's going to pull on one quadrant of the sail or another and turn it towards the sun. And so it's simple on paper, it's more complicated for real, but it's the same principle. You use so that's just for the cruise. It's what we'll do throughout the mission. But then when we need to turn to Earth for telecommunication, then we need to go faster. We need to turn the full spacecraft fast. And for that, we need to use the reaction wheels.
So you sort of warp sail in a way.
Yeah.
Like a biplane.
Exactly. Yeah, it's amazing how much you can pack in such a tiny spacecraft. We don't use the reaction control for turning, but we need it in order to escape from the Earth-Moon system. And so we are doing a relatively big maneuver. When we get close to the moon, we take the gravity assist, and at that point, we push with the reaction control system, the thrusters, to get out of the gravity of the moon. And we'll be able to image the moon. That's another thing we'll do in the process. So we hope to get cool pictures.
Any other questions? Well, you may have stumped us. This is a very interesting talk. And I just have to give a little personal note. I don't know if you know Andy Bowden. He's the deputy director of Caltech Optical Observatories.
Oh, okay.
But before he went to Cahill Building, basically, he was a young scientist at JPL. And we did have a docent trip to JPL, and he was there, of course. And when he was showing us around, he was practically beaming because, and you could tell there's something neat about it, and there's something neat about the collaboration and the science and the accomplishment. And he remembered all of that. And he was just delighted.
Yeah,
So,
I mean, yeah, absolutely. It's an amazing place. If you want to visit, if your club wants to visit, I mean, you know, when we reopen, and I don't know when that's going to be, but is that something that would be of interest? We could organize something like that.
well, that might be interesting. Yes, yeah. Well, let's keep that on the burner, if you will. Yeah, that would be a lot of fun. JPL is a really neat place.
Absolutely, yeah. We can show you cool stuff going on. We have a big mission that's being built right now, a big Earth mission with a big radar antenna. It's going to be a cool visit if you can. But I mean, we are not going to reopen to the public before maybe another 6 months.
I think you're right. And we're not even sure that Caltech students are going back in person.
Yeah. Only those that who really need access to the labs, I think, can go. So
from a JPL perspective, what did you think of the movie The Martian?
I thought that was really, so it's really cool. And my husband is an aerospace engineer. And, and so it's really hard when you're married to a navigator because you can see all the mistakes. So I just enjoy, it's cool, Matt Damon, landscape is great. But then my husband is like, yeah, no, they should not navigate the spacecraft like that. Doesn't make any sense. That's what's going on in our family. But yeah, I thought that was a really cool movie. I love it. And Andy Weir has a new book, Hail Mary, Project Hail Mary.
Mm-hmm.
It's a new book. It's really nice. The same vein as The Martian. It's about interstellar exploration.
Sounds like it's right up your alley.
Yeah, it's called Project Hail Mary. From the guy, for the Martian author.
Well, if there are no more questions, Project Hail Mary by Andy Weir.
Yeah, the guy who wrote The Martian. Yeah.
Yes, that's right. Well, if there are no more questions, I will go ahead and terminate the meeting. Julie, thank you so much for the great talk. I'm sorry I was so ham-fisted about figuring out how to display
I'm glad
the
it worked
PDF,
out.
but we managed to get it done.
Yeah, great. Thanks. I was so glad meeting with your group. I really appreciate the invite. And let's keep in touch when we have better plans, when the plans for observing NEASCOUT firm up, because it will be great to...
Yeah, absolutely. We have a big image. Scott Dixon is on the Zoom. He's the head of our imaging group. Yeah, I'm sure we'd love to pick up the challenge.
That would be cool. Thanks.
Thank you very much.
Thanks. Have a good evening, everyone.
Thank you.
Take care.
Thank you.
Good night, all.